All right, in this video, what we're going to do is we're going to go back to chapter 4. So we're going to move back to section 4.8 in your book, which is where your book introduces a concept called antiderivatives. I think the start of a Calc 2 class can be kind of complicated in that you learn a bunch of different pieces and then you don't use them immediately, and it's hard to understand, like, why am I learning this? How does this all tie together? So I teach things a little bit out of order to try to make it more logical for you. So I teach the limit stuff early on so that we can transition from estimating the area underneath the curve using rectangles to actually calculating that area underneath the curve, what's known as the definite integral. But another piece that's typically taught earlier is this idea of antiderivatives. We haven't needed it up until you get to section 5.3 in your book. So I don't like to teach it until right before then, because otherwise there's just too much stuff floating around. It's hard to keep straight everything and where it is. Anyways, antiderivatives. Here's the story here. Suppose you walked into a Calculus 1 class and you saw, I don't know, up on the board or something, an answer clearly indicated was f prime of x equals 3x squared. And you were trying to figure out, like you're trying to make notes or something, you showed up late, I don't know. You were trying to figure out what the question was. And you could see that kind of the start of this problem says f of x equals something, but for whatever reason you can't read what's written there. It's messy, it got erased, who knows. My question for you is, what was there? Right? What function, when you take its derivative, gives you 3x squared as an answer? A typical Math 251 or Calc 1 question is to provide you with this bottom line here and ask you to fill in this top line. But what we're going to do in Calculus 2 is kind of go in reverse, hence the antiderivative. We're not going from a function to its derivative. We are, informally speaking, going from a derivative to the function that created that derivative, the antiderivative. Hopefully I've stalled long enough to let you think about this a little bit. Maybe you've come up with an answer. And odds are, if you're playing along, you came up with x cubed as your answer. But some of you might have been really clever and been like, well, wait a minute, this is kind of a trick question. Because while x cubed is a perfectly correct answer, the derivative of x cubed is 3x squared. X cubed plus 49, in honor of my favorite football team, is also a correct answer. Right? The derivative of x cubed plus 49 is also 3x squared, because when you take the derivative of a constant, it just kind of goes away. So we already see how there's a bit of a challenge with antiderivatives. Namely, there are multiple answers, x cubed plus 7, x cubed plus any number, or just x cubed itself, that lead to the same derivative. And that makes sense if you think about it. The graph of y equals x cubed looks more or less like this. The graph of y equals x cubed plus 49 looks more or less like this. All it does is take the graph of y equals x cubed and shift it up by 49 units. So 49 is right here. You take this green thing, you move it up by 49, and it creates this red thing. If you think about what the derivative tells you, all the derivative tells you is the slope of the tangent line to a function at a given point. So if I pick any x value arbitrarily, I don't know, right here, whatever that is, and I calculate the slope of this tangent line, well, I'm going to get the exact same slope as if I calculate the slope of this tangent line. Shifting a graph up or down does not affect the slope of the tangent line to that graph for a given x value. So it kind of makes sense that this function has the same derivative as this function, or many, many other functions. So the first thing I want to get clear when we're talking about antiderivatives is that we're going to have to be a little bit careful with our answers. These constants are going to be kind of a pain. The way we're going to get around that is like this. Right, the question, note not the answer, but the question in Math 252 might look something like this. You might be provided with a derivative, f prime of x equals 3x squared. And the answer, not the question, but the answer in Math 252, well, the way you'll write it, or at least one way you can write it, is x cubed plus c. Typically, it's a capital C that's used here, and this just stands for any constant. This just makes clear to the reader that you understand that the derivative of x cubed plus any constant is going to give you 3x squared. Could be 49, it could be 0, it could be whatever number of your choosing. A couple other things I want to hit on. Yeah, somebody could tell you f prime of x equals 3x squared, and then they could tell you the derivative and you could tell them a function. But what if they told you the function were 3x squared and you wanted the antiderivative of this function? So the answer is still going to be x cubed plus c. But what I'm saying is, if the question didn't denote this 3x squared was the derivative, but instead denoted this 3x squared was the function, what would you put here? What symbol would you put here to make it clear to the reader that you're taking an antiderivative? Like, yeah, I get it that the derivative of this function, we write that as f prime of x. So therefore, by kind of default, f of x is the antiderivative of f prime of x. But my question to you is, what is the antiderivative of f of x? If you're thinking about this as like a chain, right? I have a function, and then its derivative, and then the derivative of that derivative, the second derivative, and then the derivative of that second derivative, the third derivative. I can keep going in this order as much as I want. So the derivative takes me up a line. The antiderivative takes me down a line. So if I provided you with the third derivative, I could ask for the second derivative and you'd understand, oh, you want the antiderivative. But my question to you here is, what's below this? And typically a capital F denotes it. So while it's perfectly acceptable to ask a Math 252 question this way, it's also perfectly acceptable to ask a Math 252 question this way. I could say f of x equals 3x squared and ask you what's capital F of x? And you'd be like, oh, capital F of x, you mean the antiderivative of this function? I'd be like, yeah, that's exactly what I mean. And the answer would be x cubed plus c. You might wonder what's next, like what's below this? There's no set notation for what's below this. So you'll never be asked to find the antiderivative of capital F of x. One more thing that kind of fits into the category of an introduction to antiderivatives and notation and stuff. It would be nice if there was a symbol that meant take the antiderivative of. Right? Like I have to write this in two different lines. I have to say, here's my question, and then the answer, f of x equals blank. Right? But I don't have a symbol that's telling the reader to take the antiderivative. I have to kind of set up a question and then ask for a separate answer. And whether I do it as indicated in red or in green, either way it takes two lines. It'd be nice if there was a symbol that meant take the antiderivative of. We have a symbol that means take the derivative of. Right? If somebody writes this, you know that they are asking you to take the derivative of x cubed, and you know to write 3x squared as your answer. This symbol means take the derivative of. What about a similar symbol that means take the antiderivative of? There is such a thing. And it might surprise you when you see it, because it's something you've seen in this class in a completely different context. When we dealt with the definite integral, we saw something that looked a lot like this. When we were dealing with the definite integral, there was a number right here and a number right here. If you ever see a symbol that looks just like that, so this weird kind of an S looking thing with the dx at the end, it means take the antiderivative of if there's no numbers here and here. So if you were ever asked this, if you just saw this, this is asking you a question. Namely, it's asking you to take the antiderivative of this function 3x squared. That's what this and this mean. And later on, we'll make more sense of these symbols, like why are these two things associated with it? Why does it look so similar to what I learned in 5.2? That's all coming. Don't worry. You'll get that as soon as the next section. But for now, I just want you to know that this right here is a question. It's asking you to take the antiderivative of 3x squared. So you can kind of think about it as this case in red or this case in green. It doesn't matter. Either way, it's asking you for the line below. Either way, it's asking you for x cubed plus c. Later on in the class, this will be the most useful form of asking somebody to take an antiderivative. But in this section right here, these two are used most commonly. Your book uses this more often than it uses this in this section, but it uses both, so it's good to be comfortable with each. One other case that I want to consider before I end this kind of intro video is sometimes you don't want your answer to be this general. This is really a family of functions, not a specific function, because c is not specified here. Right? It's all the different functions that are x cubed plus a constant. What if I wanted a specific function? What if I wanted that constant to be specified? What if I wanted the answer to be x cubed plus 49? Could I write a Math 252 question where the answer was x cubed plus 49 as opposed to x cubed plus c? And the answer is yes, you can. And let me show you how. I'd have to ask the question this way. Not only would I have to tell you that f prime of x is 3x squared if I'm using this red format. I could also do this in this green format, by the way. But following this red format, I could tell you that f prime of x equals 3x squared, but then I could also give you a piece of information about the function itself, f of x, and then ask you to find f of x. And because I told you that f of 2 is 57, you'll be able to figure out what that constant is. How? Well, you could start out doing things the exact same way. You could be like, well, f prime of x is 3x squared, so f of x must be x cubed plus c. Right? Same logic we did here. But because f of 2 is 57, I know that if I change all of the x's into 2's, 57 must be my answer. So 57 must be equal to 2 cubed plus c. And since 2 cubed is 8, 57 must be 8 plus c. And therefore, if I subtract 8 from both sides of the equation, I get that c must be equal to 49. So now I can give the reader not just a general antiderivative, a family of functions, but a specific antiderivative. I could say that f of x is x cubed plus 49. I think that that's all that I have as far as notation in antiderivatives. I just want to make the point that I didn't teach you anything about how to compute antiderivatives. I just trusted that you were able to see that the derivative of x cubed plus a constant would be 3x squared, that you remembered that from Math 251, and therefore you'd be able to undo that process. But I really didn't show you how to get from 3x squared to x cubed plus c. I just trusted that because you could go in this direction in Math 251, you'd be able to go in this direction in Math 252. But we really didn't talk about how to do that. What if this were more complicated? What if there were different numbers in these different places? What if there are sines and cosines and stuff floating around? What if there were multiple terms? Right? We spent a lot of time in Math 251 learning methods for going from here to here. It probably won't surprise you to hear that we're going to have to spend at least as much time learning methods in Math 252 to go from here to here. So what I'm going to do in the next video is we're going to start to learn some of the more basic methods for taking antiderivatives. And what we're going to see is it quickly gets very complicated, and so we'll have to keep the questions fairly simple for now, but we'll spend the majority of the rest of this class, or at least the majority of what we have not yet seen in Chapter 5, dealing with exactly this. How do you undo kind of what you did in Math 251?